Hello, Physics 103 students. This lecture is chapter 26 on simple DC circuits, kind of part two. So the first one we looked at using Ohm's law and the rules for adding up total resistances if resistors are in series or in parallel. And we're going to take a look at some circuits here that are a little bit more complex than what we saw last time. And we're going to need some different rules to be able to take care of those situations. And so when the going gets tough, you always go back to your fundamentals here. And the rules that we're going to look at today are called Kirchoffs loop rules. And we'll also look at RC circuits, where R stands for a resistor and C stands for a capacitor. What happens when you've got a circuit that's got a single resistor and a single capacitor in a series with each other. But Kirchoff's loop rules, really are not any different from, laws that we've seen before. The first loop rule really reads like this: the sum of currents entering any junction must equal the sum of currents leaving that junction. That really is just a statement of conservation of charge. If there's so many charges moving into a wire that's going to split at a junction, then whatever goes into that junction must be what's coming out of that junction when you add up the 2 or 3 or 4, how many lines, the wire gets split into. And so, that's really not that new of a concept to us. And, voltage is directly proportional to energies here, right? Where voltage is joules per coulomb. So the sum of voltages, the joules per coulomb lost and gained in any closed loop is 0. And that's really a statement of conservation of energy. And I'll show you, what a loop here means, right? Because when we look at Kirchoff's loop rules, we even see, this idea of a loop up here kind of showing up here. So, but not really new ideas. These are really just basic fundamentals. But, it doesn't take a lot to come up with a situation where what we did last time suddenly just won't work. And so this is why you're going to have these fundamentals kind of in, your back pocket to look at any kind of situation that looks, more complex than what we saw last time. So let me get this so I can kind of scribble some stuff down here. And let me just, I'd say these two loop rules for anybody that's going to go into engineering, these are, like I said, conservation of energy and conservation of charge. But, these are things that you're going to really want to know. So most of you will go on to take courses in circuits. And, this will be the basics of, how your analysis will go here. But let me just kind of come down here and scribble up some sort of very, very simple circuit here. So for example, let's say that we've got a maybe like a 12-volt battery or something like that. And, the line comes out of it, comes down here. Maybe we have a resistor here. And I'm going to call this maybe like a 4-ohm resistor. And, maybe I've got another battery in line. And I'm going to line it up this way. Okay, so maybe I've got a 6-volt battery there. And then up on top, maybe another resistor. And let's, let's call this a 6-ohm resistor here. Now, what you're looking at here is essentially a single loop. Okay, the wire is continuous, all the way around this loop, even though it might look rectangular or square. And so loop just means that you start at one place, you go in one direction, and you can return to that same spot here. And so a lot of times, that's exactly what you will do. You'll pick a spot here, and I'm going to call that maybe like location A. And what I'm going to do is go around the loop. When I say go around the loop, this is just mentally kind of go around the loop and really apply these two ideas here. Now, what I don't have here are junctions. So, a junction would be you have a wire, and then all of a sudden, the wire splits into, maybe, many multiple parts or something like that. And then, when these parts come back together, here you would have a certain current. Maybe I'll call that I1, and here you've got the same current, right? It's all got to be there someplace, somewhere. But in, this branch, you might have, you know, a different current. In this branch, you may have a different current. In this branch, you may have a different current, depending on what elements are there, whether you've got resistors, capacitors, inductors, different things could be sitting there. But, what has to be true here is that I1 has to equal I2 plus I3 plus I4. So if the current, hits this junction and breaks into three parts, those three parts have got to add up to what you started with, right? So the charge is just not leaving the wire. It's just there someplace somehow. Now, in the example that I just kind of drew up, we don't have any junctions like that. So, that rule is not going to, be needed really, because I have one loop and there's no junction. So I'm just going to have one current in there. But I am going to use this right here, that the sum of the voltage in any closed loop is 0. In other words, there are some elements there, the batteries, that can give the charged particles kinetic energy. And there are some elements there that can take away that kinetic energy. Those are the resistors. So the resistors slow the electrons down that are moving. And so, whatever energy that the charges are given by the batteries is going to be equal to the energy that gets taken out by the resistors. And they've got to add up. We have to have an accounting of joules really in our universe here. So when I come down here and look at this, I'm just going to kind of imagine that, I've got some current, and I'm just going to arbitrarily choose that my current goes that way. And so, when you look at that loop, that would be considered counterclockwise. You could have chosen that the current is going clockwise. It will make no difference whatsoever. So it's just an arbitrary choice. And if you choose, I don't want to use the word incorrectly, but if you choose a direction for the current that is not what's really happening in reality, the mathematics will let us know. So don't worry about your choice here. It's just like when you're doing kinematics, or if you're doing some sort of free body diagrams, your choice of positive and negative directions is up to you. And nature doesn't care what exists in your head or in your little diagrams, right? It's going to turn out a certain way. And if you make some choices that do not match up with the reality, math will tell you. And so I've got a single loop here. And so I don't have any junctures. And in a single loop, what I'm going to do is sum up the voltages around the loop. And they have to add up to 0. Okay. And the way that they add up to 0 is that there are positive and negative signs here. Okay. So I'm going to start at A, and I'm just going to go march around here counterclockwise. So that's what I'm going to do here. So I'm going to start at point A, and you can start anywhere you want. And I'm going to, kind of transverse the loop in a counterclockwise direction. So the choice here of starting at point A will make no difference at all to your solution. Going around the loop in a counterclockwise direction will mean nothing in terms of the overall answer here. So as long as you are consistent with what you start with, everybody's going to end up with the right results. And so it's just like choosing your positive, negative signs in a free body diagram. The final solution will not depend on those really at all. Okay. And so take a look-see here. I'm going to add up, let's get something here that actually writes here. Add up all my voltages around that loop, from A. And so what you really do, you just kind of imagine, starting at A, I'm going to go counterclockwise, and I'm going to hit, looks like 4 different elements. I'm going to hit 2 batteries, and I'm going to hit 2 resistors. This is not difficult to do, but if you mess up really one sign, then everything else is going to be really kaput for you. So you have to be just very, very careful. And it's probably a good idea to double check your signs, before moving on. And so just kind of imagine, really kind of starting right here at A, and you hit this battery here, right? And now this part of the battery that I'm going to put a little circle around, that's the ground of the battery. That's the low energy state of the battery, essentially 0 volts. And then as I go across the battery, I go from 0 volts, and then as I go across it, I'm going to sort of imagine going all the way around this loop here. As I go across it, I go from the ground up to the top of the hill. In other words, if you really transverse the battery in that direction, you would increase your voltage by 12 volts. And when I say you, imagine a charged particle starting at A, comes in, hits the ground, that's 0 volts, and then the battery kind of lifts it up and puts it back at the top of the hill. And so as you come across here, you've got 12 volts in the positive direction. You went up in energy. And if I imagine, current coming this way, because that's just what I chose here, I just kind of imagine that the current's going that way. And I didn't have to imagine that at all that way. I could have had it going the other way. But if it's going that way, then the charges here in this region have yet to hit that resistor. So they have more energy, right? They've got more energy. And when they flow across that resistor, they have a reduction of energy. And what's in the back of my mind here is something like Ohm's law, V equals IR. And so the voltage drop as I go from right to left here, and it's a drop. So it's a drop, add them all up, and I would have the current times 4 ohms. Well, where did that come from? Well, that's just this right here, V equals IR. Right, this is voltages around the loop, and I'm just looking at going in a single direction. Makes no difference which direction you're going in, but you have to know, am I going from high energy to low energy or low energy to high energy? And that's what you really want to do here, because right here you've got really high energy, the charges do, and when they go across, they meet some resistance, and now they've got lower energy. So they reduce their energy, and that lower energy is this minus sign. When I went across the battery, if I'm a charge coming across the battery, I gained energy. And when I gained energy, that's the plus sign. So the battery giveth, going across that resistor, took away. Okay. And so I'm going to keep going, add them all up. I've got 2 more elements. And as I'm coming across here, the next element that I run into is the battery. Okay. And now this battery, this is high energy side, right? That's the top of the battery. This is the low energy side. So as I go across it in that direction, I'm going to a lower energy state. A lower energy state. I'm going to 6 volts less when I cross the battery. And so when I cross from high to low, I lost 6 volts of energy here. And then I'm going to have to add all these up. And then I've got to cross, this last resistor right here. And if the current really is going in this direction, and I don't know that it really is, but if it's really, coming through all of this stuff here, and it's coming in this direction, then it has yet to cross that 6 ohm resistor. So this would have to be the high energy side. And when, the current goes across it, it knocks some energy out. So that's the low energy side. So I'm going from high to low. So I'm losing energy. And so I've got my current, whatever that is, going across a 6 ohm resistor, so V equals IR. That's the way these voltages really kind of add up here. and so they have to add up to 0. And so, before you go any further, it's always worthwhile to check your signs here. Okay. And so I'm going to do that right now. So make sure that these signs make sense. I'm going to start at A, and when I come across this battery, I'm going from low energy to high energy. Okay, increasing energy, I've got a plus sign. And as I come across this resistor, I'm going from high energy to low, so I lost energy. As I go across that battery, kind of backwards, right? You're kind of going from the high potential to the low potential. You're going kind of backwards through it. That's a minus sign. And if the current is really flowing the way that I've got it, then this would be the high energy side of the resistor. And then once I cross the resistor, if the current's going that way, then I'm hitting the low end. So I've got a loss here. And so I think, these signs, kind of are working out whether I'm gaining energy or losing energy. If I'm a charged particle, I'm really going in this direction here. So what I've got here is 12 volts. And on the other side of the equal sign, I've got 4 times I. That's this term, so I'll add that to both sides. I've got plus 6 volts. That's this term. And then I've got this term here, 6 times I. And so I'm going to subtract that 6 volts from both sides and get 4I plus 6I, that's 10I. And so 6 volts divided by 10 is the current in this loop, which is 0.60 amps. Okay. And notice here that I'm not writing it down, but there is an implied positive sign here because everything else is positive. That positive sign, what it really means is I just guessed at which way the current was going and I solved for the current. And if I get a positive sign, that meant that I chose the direction correctly. So the current, or the current's actual direction, is as I guessed. Okay. Now, looking at that little circuit here, it kind of makes sense, right? You've got 2 batteries. You've got a 12-volt battery and a 6-volt battery, and they're really kind of pushing charges towards each other. So when I first looked at that, it kind of made sense that, well, the 12-volt battery is going to win, right? It's got a higher potential, and so, the net flow is going to go in the direction that battery is really pushing. And a lot of times that intuition serves you well, sometimes it doesn't, but the math would tell us. So if we got a minus sign here, that if we had the current is minus 0.60 amps, that would mean that the current is just going in the opposite direction than what I really kind of thought it was doing here. But that's the idea, is that here I have a single loop, so I have no junctures, so I didn't have to worry about that loop rule. But as I went around the loop, and it doesn't make any difference which way you go across each element, and figure as I go across the element in a certain direction, am I going from a higher energy state to a lower one, or from a lower one to a higher one, and that determines whether you've got plus or minus signs here. Now, if you started at point A and say you went in the other direction, what you would have here is exactly the same equation I have, except every element would have an opposite sign of what I've got here. And I can change all the signs here just by multiplying everything by -1. And when I multiply the other side of the equal sign, which starts off at 0 by -1, nothing really changes, right? So you can see that the direction that you transverse the elements in your thinking really has no bearing on what you really get for an answer here. So what makes sense is to look at maybe one step more complicated situation here, where we have more than one loop, so we'd have maybe junctures, and then kind of see how to use these rules here, and maybe something a little bit more complex. I think you've got probably this example in your package of materials here. Okay. So take a look-see there at this one. And so it looks like, what you really have here are 3 loops. There's a loop on the left, there's a loop on the right, and then there's really the outer loop. Okay. And so, people that get really good with this stuff, would use these loops, very nicely to their advantage, looking ahead at how the calculations go, because they've got a lot of experience and so forth. So I do have junctions here, and so I'm just going to pick a junction and arbitrarily choose some currents, coming and going and so forth here. So I'm going to choose this spot right here. So there's a junction right there. Okay. And I'm going to imagine on the right-hand loop that a current is coming into that. Okay. And so I'm going to imagine that there's this current coming into it, and I'll just call that, I don't know, maybe I3, because I'm going to imagine some current leaving this. I'll call that I2, and then maybe some current leaving this right here. I'll call that like I1 or something like that. And the only reason I'm calling them I1, I2, I3 is that they are different values. But take a look at what's happening. I3 comes into the juncture, and then the other two currents leave. And so the one loop rule allows me to write this down really immediately, that I3 has to be equal to I1 plus I2. That's conservation of charge. There is so much charge, I3, coming into the loop. All the charge then has to be leaving that loop. But that right there, that's key, because what is that? That's one equation, and immediately you see that there are three unknowns. And so this is still not a very complicated situation. You can see all of a sudden I've got three unknown currents, because there really are three single lines in here, right? I've got the line from the junction going to the left, I've got the line from the junction going down through the center, and then I've got the line coming into the junction. And so all three of those will be carrying three different currents, and we've got to find all three of them. So what that really means is that we need two more equations to be able to get three equations and three unknowns and be able to, work this through here. And so I'm going to do, just kind of what we just did a moment ago. And I'm going to go around the loop, and I'm going to now probably be adding up something like voltages. Okay, so just kind of keep your work always kind of nice and neat, and so you can kind of follow exactly what's taking place here. But I'm going to take a look at that left loop and see if I can't get some equations there. Okay, so let me call this here point A. That was, the juncture that, I had currents coming into and currents coming out of. And you could have picked the bottom juncture and did exactly the same thing. Once again, how you do this, really in the long run will not make a difference here. Okay. And I'm going to go in this left loop, and I'm going to transverse it. Counterclockwise. So that's in the direction of I1 if I1 truly is going in that direction. And so that means I'm going to do the entire loop. Okay, so I'm going to start here at A. I'm going to go across that element, that 2 ohm resistor. And I'm going to come down here. I'm going to go across that 3-volt battery. I'm going to come and go across that resistor there. And I'm going to come up and go across that battery, and then go across that resistor and get back to A. Right? So you got to do a closed loop. So you got to start somewhere, get back to there, and you just choose a direction. And so I'm just going to go counterclockwise here. And what I'm going to do is add up my voltages when I really sort of do that here. Okay, so the idea here is I'm going to sum the voltages over the left loop, and they have to add up to 0. So I'm going to go across 2 batteries there. So these batteries, are pushing charges, and so there is something there that is giving you energy, and then resistors are taking it away and so forth. So, so let's add these up on the left loop. And the first element that I run into is that 2 ohm resistor. Okay. Now, if I1, my current that is in most of that loop, right? I1 is in the single line here. that, let me see if I can get rid of this. Yep, okay. So everything that's yellow right there has I1 in it. I2, the second current, is in that middle little wire that's connecting the two loops here. Okay, so in this loop, I'm going to go across 3 elements with I1. Okay, so if I1 really is going in this direction, then on this side of the resistor, that's kind of high energy, because it's when you cross the resistors when the brakes are being put on you. And so this is low energy here. That's the low energy side of the resistor if the current really goes that way. So as I go across it in that direction, I've lost energy. So I've lost how much energy or how much voltage I've lost. So it's a minus sign. I1 times 2 ohms. So V equals I times R. There's I, there's R. And that plus or minus sign is, did I gain or lose by going in that direction? Add them all up. And as I'm coming across here, on the battery here, right, this is the high energy side, and this is the low energy side. So as I cross it going this way, I'm going down in 3 volts. So I went down in 3 volts. Add them all up. And as I keep traversing in this direction, if the current really is coming this way, so if the current really is coming this way, then this is the high energy side, and the current then goes across the resistor. This is the low energy side. So I am losing I1 times 2 ohms. Okay. So those are my 3 elements that have I1 in them. Then I'm going to, I'm still transversing, the loop this way. And now I'm going to go up this middle line. So I've got 2 more elements. So I'll have 2 more terms here. And as I cross that battery, notice that this is the low energy side, and this is the high energy side. So if I go across the battery that way, then I see charges gaining energy. So that's plus 6 volts. And then I've got one last element. And so if I2 is actually coming this way and I'm moving this way, here the current has crossed the resistor already. So that's low energy. And then I cross into this region here where the current hasn't quite got across the resistor yet. That's high energy. And so the charged particles I find there have a higher energy state because they've yet to be slowed down by that resistor. So as I cross it, I'm kind of finding things that are going faster. They hit that resistor, and then on the backside, I'm finding them going slower. And so they're going up in energy. And so that's going to be I2 times 4 ohms. And that has to add up to 0. And, let's see what this gives us here. I'm going to combine this and that. And so 6 volts minus 3 volts is 3 volts. I'll get this term and put it on the other side. And just to clean it up, I'm going to drop units. So I'm going to have 2 times I1. And this is going to go to the other side of the equal sign 2. So that's 2 times I1. So that took care of that term, and that term. I've taken care of that term. And then when I bring this term here to the other side of the equal sign, there's a minus. So I'm going to subtract that from both sides. 4 times I2. Okay, so what I've got here is 3, and 2 plus 2 is 4. I1 minus 4 times I2. Okay. There's not too much you can do with that algebraically. It's one equation, there's 2 unknowns, so you really can't, quote unquote, solve it. I think we've got it probably about as simplified as it's going to get. So I think just kind of leave it there, right? And for the most part, you all can do the algebra here. The algebra is not hard. Just always make sure you go back and look at all your signs. So one sign mess up here, and everything is going to be really kind of kaput. And so what I need here is another equation, because I still have 3 unknowns and I only have 2 equations here. So now what I'm going to do, I'm going to go around that right loop. Okay, and when I go around the right loop, I'm going to add up all the voltages on the right loop, and I'm going to add them up and set them equal to 0. And so, I'm going to start at A. And I'm going to transverse, and that's just, when I say transverse, that's just in my head, clockwise. So I'll just go clockwise. So in other words, I'm going to start at point A, and I'm going to go this way around that loop, and then get right back to A. And when I say I'm going to go around, I'm just looking at, am I gaining energy or lessening energy by moving in that direction? So if you move in the other direction, you'll get exactly the same equation with exactly the opposite signs, and you factor out a -1, and we end up with all the same equation anyway here. So, so that's the idea here. So I'm going to see if I can't keep my eye on exactly what's taking place here. So I'm going to start at A, and I'm going to come this way, and I'm going to go across that resistor. Okay. But now take a look at how I chose the direction of I3. So if I3 is really coming that way, this is the high energy side. This is the low energy side of the resistor. So if the current really is coming from right to left, on the right-hand side, before it's hit the resistor, the charges are kind of moving faster. If they hit the resistor and it slows them down, we take out some kinetic energy, and that resistor then is having some work done on it. And then you get to the lower energy side. So when I go clockwise across it, I'm going from the low energy side to the high energy side. And so that's a 2 ohm resistor with I3. So I'm going to add up all my voltages on that right loop. And it looks like I'm going from low energy to the higher energy side. So that's a positive sign. I'm gaining energy. And once again, as I look at that, that's I3 in 2 ohms. I3 and 2 ohms. Okay, add them all up. The next element that you traverse, that you hit, is that battery. Okay, now the battery, this is the high energy side. That's the top of the battery, and here's the low energy side. So as I cross it in this direction, I'm going from high energy to low energy. So I'm losing, right? So if a charge actually went from the top of the battery to the bottom of the battery, it went from the top of the hill to the bottom of the hill. And that's a difference of 6 volts, -6 volts. Add them all up. Then I'm still traversing, and I'm going to run across this element here. Okay, so I have guessed that I3 is coming this way, the current in that particular wire. And so if it's coming that way, this is high energy side, because if the current's coming that way, it has yet to cross that resistor. And once it crosses, right, you got a bunch of braking going on there, then that's the low energy side. So as I cross it clockwise, I'm going from low energy charges. Then on the resistor, I go to the other side, I find higher energy particles. They're going faster. And so that's going up in energy. And this is I3 with a 2 ohm resistor. So plus I3 going across a 2 ohm resistor. And as I keep doing this loop here, going in this direction, there's no elements here. And now I'm going to go into this middle section. And as I keep transversing in this direction, I'm going from low energy to high energy, going from the low energy side of the battery to the high energy side. So if I actually were charged and I cross that way, the battery would give me 6 volts. Right? So I'd have plus 6 volts there. And then I think I've got one more element here. So we've got I2 in here. So we've got I2, and I'm going from, if I2 is really kind of coming towards me, I'm going from low energy side. This is the low energy side of the resistor, because that's where the current has already come across. And so those charges are moving slower. And I cross it, I find that they haven't yet been slowed down, so they're going high. They're going faster. That's the high energy side. So that's a plus sign. So that's I2 4 ohms. I2 4 ohms. I2 4 ohms. Okay. And so that's going around the loop, set them equal to 0. And I see I've got minus 6 volts plus 6 volts. That seems odd, but yeah, those are both 6-volt batteries. So, okay. And I've got an I3 and an I3 and an I2 here. So I'm going to combine those I3. So I've got 2 of them plus 2 of them. So I've got 4 I3s equals 4 I2s with a minus sign. In other words, I'm going to get this term right here and also put it over on the other side of the equal sign, and so then it has a minus sign here. Okay, and so what that means, I'll get these 4s and cancel them out, is that I3 equals I2 with a minus sign. Okay, so when you kind of go through a lot of steps like this, you always want to check your signs. Always go back and just double check, because the algebra is not hard to do, but you want to make sure that everything here is looking pretty good. Now what this means is that the size of I3, how many amps it is exactly the current that is in I2, except the direction is not correct, right? So they're in opposite directions or something like that. But now I've got maybe 3 equations here. And so we can start substituting and kind of playing the algebra game here. So, just to kind of go through one of these from top to bottom. We've got that equation. We've got this one right here that says 3 equals 4I1 minus 4I2. Okay. And then using the junction rule, we started with I3 equals I1 plus I2. I3 equals I1 plus I2. Okay, now we can get another equation here. And so if we need to, we could do the outside loop and leave that little middle section out. But this might be enough to be able to, maybe get some sort of solution here. And so, let's see here if there's anything clever that we can do here. I3 equals minus I2. But I3 from this equation also equals I1 plus I2. And so if I get this right here and I move it over here, I'd have minus I2, and I would subtract another I2 equals I1. And so I guess this is minus 2 of those currents equals I1. And so now I have one equation right there with 2 unknowns. So I've used really, this equation, and I've used that equation. So there's probably no more use out of those 2 equations. Now I'm going to get this one here that I just came up with and combine these results here with this equation that has yet to be touched there. Okay. And so I should now be eliminating, variables and so forth here. So, doing this algebra is never really pretty here, but I'm just going to start with 3 equals 4 I1 minus 4 times I2. And I'm going to probably just do a substitution here. And I1, I'm just going to substitute in, is the same as minus 2 times I2 minus 4 times I2. And just solve that equation. Let me make sure that I don't have any, algebra snafus here. So 4 I1s, 4 I2s, I'm going to substitute out I1, and that's really, I think I want to write it this way. And I think that looks a little better algebraically here. Okay, so I1 is the same as 2 times I2 with a minus sign. Okay, so now we've got one equation and there's one unknown. So now you've actually got a fighting chance to really kind of solve this here. And so let's leave that 3, bring that 4 in here. And I guess you get minus 8 I2s minus 4 I2s. And so just take it piece by piece. So is that minus 12 I2s? And so 3 divided by minus 12 equals I2. So I2 is negative 3 divided by 12. I guess that's 1/4 here, right? So 0.25 amps here. Okay. So the magnitude of the current is 1/4 of an amp here, 0.25, okay? And now I have this minus sign here, and what that minus sign means is that when I go back to what I decided when I started doing this calculation, that I chose I2 to have a certain direction, and I2 is sitting like right here. Okay, and so I said, well, it's really kind of coming, or leaving that junction. And my calculations say, no, it's really going in the opposite direction. Okay, so it's really kind of coming up. And so my direction is not quite right, but that's okay. So that just means that the direction is, kind of opposite of what I've got here. And then, you still need to keep doing some algebra. Now that I've got a value for I2, maybe I'll come to this equation here, and minus 2 I2 equals I1. And I2, we can put in a value here of 0.25 amps with that sign. This is I1. And just do the algebra here. Negative times a negative is a positive, but 2 times 1/4 is 2/4. And so like a half an amp equals I1. Okay. And then you can use then another equation to end up getting I3. And so this means that the direction that I've got, I1 going in my original picture was the correct direction. And then I've got an I1 and I2. And so the only equation that's got I3 in it says I3 equals I1 plus I2. I1 plus I2. So that's an equation from above. And so we can get I3 from that. And so this is 0.50 amps. And I2 with my signs and my directions has this minus sign. So I'm going to keep that here. And so I guess I get positive 0.25 amps here, looks like. Okay, so it looks like, when I was guessing the currents, I got 2 of them right. One of them is not. No harm, no foul. You can get them all the directions wrong. And then you just have minus signs running around here. Okay, so that's the idea here. So Kirchoffs loop rules are actually very, very powerful because in theory, they should be able to handle just about any sort of situation because you're just conserving energy and you're conserving charge, and you really can't get more basic than that. Okay, but you can see here that very easily you can have 5 or 6 or 7 or 8 different unknowns, and those unknowns are your currents flowing through different parts if you have, you know, a lot of loops and so forth. And so, you know, usually when you'll take some sort of circuitry class, you know, somebody's going to remind you probably of Kramer's rule and, you know, using determinants and things like that to do many equations and many unknowns at one time, so that you can do these things, you know, you know, fairly quickly. And, you know, that's sort of the idea. And so it's something that you probably did in a high school, you know, algebra 2 class or something like that. You know, you'll probably get reminded on how to do a lot of that stuff here. Okay, so, but that's the idea, that you go around the loop, choose a direction, hit your elements, and just, you know, look at the situation by going from the high energy side to the low energy side, then you're losing energy. If you're going from low energy side to high energy side, then as you transverse it, you're gaining, you're going to the higher energy side, and so those will become positive signs in your voltage equations. I think what I'm going to do now is probably use Kirchoffs loop rules here to look at a very simple circuit. And but it's got very interesting mathematics here. And the circuit has got one resistor and it's got one capacitor. And that's called an RC circuit. And there's very interesting mathematics that come out of that. And I think using the loop rules, we should be able to, you know, determine how to analyze that situation, and then just plow forward and just use brute force and do the math and kind of see what we can learn about something like this. So a couple of man-made devices. And let's take a look here at RC circuits. So usually in an RC circuit, you're going to have 3 elements. Okay, so you're going to have a battery. The charges come out of the battery. They go across a resistor. They hit a capacitor, and that is the circuit. Right? It does not look that complicated. So here's a voltage source. Here is the resistor. Here is the capacitor. Okay? So you have a V, you have an R, and you have a C here. Now, what's interesting about the physics here is, you know, imagine that you haven't really quite connected the wire to the top of the battery yet. And so there is no charge flowing whatsoever. And the capacitor starts uncharged. So it's completely no charge on it. And just as you hook up the battery, okay, at that moment, we call that just T equals 0. At the start here, there is really no charge really kind of going across the capacitor yet, right? In fact, the charge never goes across the capacitor, but I should say is that there's no charge on the capacitor. But inductively, as you throw a charge on one plate, it kind of throws a charge off the other plate. And that's just coming from the Coulomb repulsion, you know, between charges and so forth. But when you look at this right here, you know, just do something like this. Apply I only have one loop, so there's no juncture, so I don't have to use the junction loop rule here because it's insignificant, right? We don't have any branches or anything like that here at all. And so, you know, if we start here and we go, you know, this way around the circuit, I'm going to guess that the current, since this is the top of the battery, is going to be going that way too, right? So I'm going to guess that my current is going that way. And so as I go around the loop here, you know, I hit the battery, I go up in voltage. And then if the current is really coming this way, here it has yet to cross the resistor. So as it crosses, you know, this is the high energy side of the resistor. Here's kind of the low energy side of the resistor because they've been slowed down there. So I've lost some energy. Okay. And then how do I write voltage losses or differences, in a capacitor? And so, I told you to always kind of remember this, that, Q equals C times V. And so Q all over C equals voltage. Okay. And so, we've got something like that. Okay. So this right here is the equation, right? That's what we've got to deal with here. And so when you start looking at something like this, start breaking apart your thinking into nice little bite-sized chunks here. And I'm going to sort of do that here. I'm going to say, at t equals 0. And here's why we're doing this here. In this equation, we have this voltage. That's the voltage of the battery. Essentially, it's just a constant. Okay. And so that doesn't really change, right? The battery is what the battery is. However, that right there, that I, that's the current coming from the battery, right? And it's variable. When I say variable, it starts off as big as possible. And then it becomes smaller and smaller and smaller and smaller. And that's because as charges flow from the battery, they start landing on those capacitor plates. And the more charges you put on the capacitor plates, the harder it is to put the next one. And so the current gets smaller and smaller and smaller until you fill the capacitor, and the voltage across the capacitor is the same as the voltage of the battery. And then all of the current stops. So it's variable from I0. Let's write it that way. I0, your initial current, and it's going to go all the way to 0, and that's when the capacitor is full. Okay, so I here is not a number, it's a number, I0, whatever that initial value is, and then it goes down to 0. And so it gets harder and harder to keep putting more charge out. R, this is a constant, right? That's just the size of the resistor. So that's a constant. This C right here, this is a constant. C is a constant here for a capacitor. It has a certain capacitance. But this right here, Q, this is a variable. At t equals 0, if there is no charge on the capacitor plates, then Q is 0. You start with no charge, and then it builds up, and Q keeps becoming a bigger and bigger number until you hit this maximum that you can have. So at t equals 0, Q equals 0. This is for an uncharged capacitor. Right? And that's the way they typically come. And so there are two foul beans in this equation. I and Q essentially are functions of time. Okay, that's something that is very interesting. And so I had you kind of look at, a cheesy little lab where, we might have a light bulb, a resistor, and then a capacitor, and then somebody measures that the light bulb stayed lit for a certain amount of time. And that means, the current is going across the battery, and eventually it stops. And so eventually I goes to 0. So this was to be prepping you conceptually that, I, in this case, because of the capacitor, the current is not a constant, right? It's changing. And so if you did this activity right in front of you, and you watched very carefully, what you would notice is that the bulb is brightest immediately when you hook up the battery. And then it gets dimmer and dimmer and dimmer and dimmer, and then it goes out. And then you can't see it really glowing anymore. And maybe you see it glowing longer if you turn off all the lights in the room and you're really, in a pitch black room, you might see the filament just kind of glowing and stuff for a while. But it's telling you that I and Q are functions of time. That is really key here. Right? So that's something that you've got to pay attention to here. In an RC circuit, typically I and Q are functions. Okay, now, can you tell me what those functions are? Well, we're hoping that our physics can do exactly that. And so we'll get to that here in a moment. But let's once again kind of look at part A here. At t equals 0, we'll kind of look at little bits and pieces here, and see exactly what's taking place here. So at t equals 0, there is no charge on the plates for an uncharged plate. Okay, so what does this mean here? If Q is 0, and I've got this equation that is describing my physics, that's 0 when t equals 0. So I'm just going to kind of throw that out of there, and what I end up with is this right here. And so that current is when t equals 0. And so I'm going to call that my initial current. The initial current is as big as it can possibly get. And so your initial current is that right there. And you might just call that I maximum, because it's going to start from there and then it's going to wind on down to 0. Okay. And we'll take a look at what that function here is in a moment. Okay. And so if you look at the start of the process at t equals 0, this is the kind of information that we can kind of glean from that. Okay. And the other place that we can maybe get some easy answers is when the capacitor is full. When the capacitor is full, I, which is a function of time, goes to 0. The current stops flowing. Okay, so I'm going to go back to my my original equation here. I've got the voltage IR minus Q times C. Okay, and those add up to 0. And I'm going to let this current, which is a function of time, be equal to 0 when the capacitor is full. There's no more charge flowing. And so, this piece right here of the equation just kind of drops out. And what we get is something like this. Right, so I'm going to get Q, C, I'll multiply it, across. And so, what I really have here is Q. When it's filled up, that's Q max, and that's really C times V, which is probably not a surprise, right? This right here is a form of, right there, that's a form of Ohm's law. This right here is not something new either, right? That's just the general descriptor of any kind of capacitor, right? Q equals C times V. And so once it's charged up, we have exactly the result that we really started with, a couple chapters ago, and we just assumed that they were kind of, charged up, and there was charge there. We were starting to talk about things conceptually and so forth. Okay, so this is the the two places where it's easy to really kind of deal with the situation. At the start of the situation, when you have no charge on the plates, I can see exactly what the initial current is equal to. V divided by R. The other place is when the capacitor is full. That means that there is no more charge coming into it. There's no more current. And so then I can solve for, looks like in this case, exactly what is the maximum amount of charge that can be put there. That's C, and usually the capacitance depends on two things, right? The geometry of the plates and whatever materials you put in there, and then the voltage of the device that is actually pushing the charge. And so how much charge you can put on the plates is proportional to the, the pusher, the voltage source, as well as, what kind of capacitance you've got built into the plates and so forth. So yeah, this is all very nice, right? That things work out here, very, very well. So, and I think no surprises there at all. Okay. So let us go and actually solve the equation. So let me just kind of start here on a new page, and let's actually solve this equation if we can. And the equation we're going to solve is, V minus IR minus Q over C equals 0. Okay, so there is the equation that, we've got to kind of solve. And the two troublesome terms in here, is this I, that's a function of time, and how much charge is on the plates is a function of time. And so what we're going to do here is that we're going to solve the equation for charging the capacitor. And so I think what we'll probably do is, start off with the idea that, it starts with no charge, but, eventually I don't think that'll make too much of a difference or anything like that here at all. Okay. And so let's just get our equation here in front of us. And really the issue here is that I and Q are functions of time. And so it's like we have a function right here in front of us, and there are two functions down inside of there. And so there's just too many things that are, variables here. And so probably the best thing to do is to be clever and remove, one of these variables here. And probably the best thing to do here is recall the definition of current. And so this might be kind of coming to your mind here, right? That current is the amount of charge per time, right? Amps is coulombs per second. And make that substitution in here, and let's just sort of see what that leaves us here. So I'll just kind of leave this term here alone. Let's just do kind of one at a time here. And so I don't want an equal sign there, I want a minus sign. So minus, and this right here is dq dt. R is a constant. And yeah, I don't know. I think maybe I'll just get this Q and C and put it on the other side of the equal sign here. Okay. Now, this doesn't look great to me, but maybe it's not really, awful or something like that. But I'm kind of, sniffing out that there are some, since I've got this fraction here, either I'm going to multiply everything by C to clear that, or I'm going to do something here. But, I've got a Q here, and it's a dq, so it's a differential. So since it's an over dt, it's a full-blown derivative. And I've got a Q there. So eventually I'm going to want to have all those Q's probably, all on one side of the equal sign here. And so let's, I think to start clearing some variables here, I think I'm going to go from here to there. And there's two things you can try here. I'm going to divide by R. So I'm going to just divide all the terms by R to clear out this R here. So I'm going to divide that term by R, divide that term by R, then divide this term by R too. And so, when I do that, I think I'm going to end up with is something like minus dq all over dt. So these two r's will cancel. And then over here, I've got q with an rc. And then I'm going to minus this v all over an r there. So I'll get this, and I'll subtract that from both sides. And so I end up with something like this here. And once again, the only thing that's really at my disposal right now with the level of math that most of you have is to try to get my differentials and separate them. That is a separable differential equation. And then I could integrate both sides. So there are other techniques to differential equations here, but we really only have one. So with that in mind, I think what I'm going to do here is write this side all over a common denominator, which is RC. And so on the top here, I need to add a factor of C. Right? So if I write it that way, then this looks probably pretty good. And so what I can do now is get all of the Q's on one side. So I can cross multiply. So I'm just going to leave this minus dq here. And I'll divide both sides by this q minus v times c. So now I've got all the q's on one side, which we really kind of need. And I'm going to multiply both sides by dt. And then on the bottom of that, I've got rc here. Okay, so I've got something like that. Okay, so this minus sign that's floating around here, it's probably traditional to put it on this side. So I'll just divide both sides by -1 and kind of get rid of that there. And now what I have are my two differentials, dq and dt, but they're on separate sides of the equal sign. Now what I can do is get rid of the differentials by integrating both sides. I want to integrate both sides, right? I've got some functions here that may be hard to integrate, might be easy to integrate, but theoretically this is doable, right? So I should be able to do that now to both sides. And one side, the right side, is a integral over time. The other side is an integral over charge. So here I'm going to go from 0 to t, and that little t just stands for any time at all, any time that we want. And my charge, I'm going to start with charge being 0, and it just goes up to some value q, and eventually it goes to q max, right? Whatever the maximum that this capacitor can hold with that battery pushing charges. But that's what I'm going to do. It's just to have a dummy variable for q, little q, and then a variable here for time, and I'll just call that t or something like that. Okay, now one side of this is easy to handle because this right here, RC, is so this RC right here, the resistor is a constant, the capacitor is a constant, so those pass out of the integral sign, and so you've got that right there. And even I can integrate that, right? So I haven't, taken the course in integration in quite some time, but the integral sign here will undo the differential, and then I evaluate here at my limits of integration, and so it's t, and I go from 0 to t, and you just end up with this minus t all over RC here. So one side is really done. It's the other side that might be a problem here. And you've got an integral over dq, and you've got a q down here in the bottom. And so I don't know what the best thing to do here would be. There might be something clever, but I'm kind of thinking maybe some sort of u substitution to start with. You can sort of try something like this, and then when you do du here, you're going to get a dq, and then when I make that substitution here up into there, maybe I've got an integral here, and so I've lost my limits, right? So I'll have to go back to my limits here in a little bit. But du equals dq, so dq can become a du, and then on the bottom I just have a u. Okay, that's something that I can integrate too. So you make up an entire function just to be able to do that. That's a natural log, right? And so this comes out to be a natural log of u. And but we do have these limits of integration here. So that's something that you've got to really kind of keep in mind here. So I think what I'm going to do here is just write it like this, and then u is q minus c times v. So now I have substituted back, and then my limits of integration, are from 0 to this little q or something like that. Okay, so we still have to worry about the limits here. So there might be maybe some different ways you can write this that might make life a little bit better. I don't know. But let's just maybe put those limits in and kind of see what we get here. So I get this little q minus cv, and then I put in the other limit, which is 0. And so you have minus the natural log, and I put in 0, so it's just c times v. Okay, so it doesn't look great to me or anything like that, but I think I'm going to write this as 1 natural log. And so I've got q minus cv, and then what that minus sign means, I divide, and then on the bottom I've got minus cv. And so that makes things a little bit more compact here. So I think once we put in the limits, we can write it this way. And there's really nothing wrong with natural logs. They're just fine. Typically, people don't deal with them, and that's just kind of a choice. So we can get rid of the natural log. And so, if you really want to get rid of the natural log, you're going to raise both sides to the e. And so, these two functions essentially are inverse functions. And, that will leave you with, maybe something like little q minus cv all over minus cv equals e raised to this power right here. Okay. And so I'm just going to kind of keep, playing with this here step for step. And I'll multiply both sides by that minus cv. And so this q right here, this is really a function of time. And so that equals cv minus cv with all this stuff here. And so maybe I'll write q here, my function of time, as cv. And maybe I'll just factor this out here. Maybe that might make it a little bit easier to really kind of look at here. And the charge on the plates is a function of time. And so if I put in t equals 0, which we already did, right? If I put in t equals 0, this term right here, you should have an idea what's going to happen. If I put in a 0 there, something magic happens to that term. You take a look at that, and that should match up exactly with what we did before. And remember, c times v, this is another name for what we called q max. And so we could write it this way. And this is really kind of a thing of beauty here, that as you are charging the capacitor, what is going on here is that you are building up to some final value, and that's q max. Okay, and so when you put in t equals 0, you really get a 1 for that one term. 1 minus 1 is 0, so the charge in your plates is 0. That seems to match up. Now, when you take a look here, as t goes to a very big number, when t goes to a big number, that exponential starts going towards 0. 1 minus 0 is 1. 1 times q max, and you're building up to q max. So really this function starts at 0 and it builds up to some sort of value or something like that. And so I'm kind of imagining here, what is taking place is something kind of interesting. That if I, look at time here, and, I look at charge as a function of time, really the charge starts off at 0, and, it starts building up to some maximum value, right? And so this right here is like Q max. And, you kind of get closer and closer and closer to something like that. Now, the people that get really good at this, what they notice is this right here. R times C shows up in this function, and R is a constant and C is a constant. Okay, and so that is really determining how quickly you get up to this maximum value. And so R times C is referred to as the time constant. And a lot of times people will call that tau, R times C. And then they get really good at looking at one-time constant, two-time constants, and when you start putting in, 1 or 2 times those values, you start seeing exactly where you are in this curve and things like that. So you're going to see a little bit of that, probably in your reading here, for sure. So the charge on the plate starts at 0, which we kind of thought, and it builds up to Q max. But it's this exponential, right? And it's a limiting exponential. So it's really kind of building up to that maximum value. So very interesting that something like Kirchoffs loop rules, just add up the voltage around the loop, gave us enough information to be clever enough to actually write eventually a separable differential equation, which then leads to this result. And so we have a function for Q as it builds up on the plates. And so the battery looks like has an easy time early on, and then it gets harder and harder and harder to start putting more and more charge on these plates here. Okay, so we said that Q was going to be a function of time. The other function of time was the current. The current starts off big, right? The battery has an easy time up front, but the more charges that piles up on the one plate of the capacitor, it's harder to put more charges there because you have this repulsion of kind of pushing back on the charge that you're trying to push downstream. And so the current is also a function of time. And so let me see what I call this here. I just sort of call this number 2, solve equation, charging the capacitor. Okay. And so number 3 here, we're still charging the capacitor. And what we want here, is the function of time of what the current looks like. Okay, so I've got a function for the charge on the plates, and so what I really kind of want here is, what's the current really doing here? And I think what I'm going to do is just kind of write down what I've got, up in the step up above. I've got Q max, and then times this function here. That looks like that. And I think what I'm going to do here is just kind of remember, right, that charge and current are very closely connected, that I equals dq dt. So if I take the derivative of both sides with respect to time, that should be the current then. So that is, if I take the derivative of this function with respect to time, that is defined to be the current. And that'll be a function of time. And so I've got to take the derivative of all of this garbage here. Right? With respect to time. And then that would be my current function of what the current happens to be doing. And so I'm just using a definition there. I'm just going to hit that thing with a derivative with respect to time. Now, when I multiply this in here by that, Q max is just a number. That's a constant. So when I take the derivative of that, that thing just really dies off to nothing. And so it's when this gets applied to that. So I've got this minus sign, and you've got really like Q max times E minus TRC. And I'm hitting all of this with this operator, right, this DDT. And so when you take the derivative of that, you know, what ends up happening here? Yeah, good. So what do you get here? My t is inside of a function, so I think you have to use the chain rule. So I think you get, you know, this full function here, right? You're going to get that full function times the derivative of the stuff that's on the inside, and that might be like 1 over RC when you differentiate that. So there's two minus signs here, so maybe I'll just get rid of those. And I have Q max out front, and then I've got this RC, and I end up with something like that. And you know, there's a couple ways, you know, you could leave this just exactly like what we've got here, but remember the voltage of the battery equals Q max all over C. So these two pieces right here could be just written in terms of the voltage of the battery. So V all over R, and then you've got something like this. Okay, and so there is the current for a charging capacitor. And, you know, what are you looking at here? This is an exponential decay. And so, you know, if we were looking at this in terms of what's going on with the functions here, here's I, and it's maybe some sort of function. You know, you start off at some value here, and, you know, here's time. You start off, and then in this value here, so at time 0, I'm guessing this would be equal to, you know, V all over R, and it just starts dying down like that. Right? You have an exponential decay. And once again, the people that really use this quite a bit get very good at looking at controlling this circuit with the values of R and C. Because R and C, once again, is the time constant. And so how fast this function dives down to 0 or how slowly it goes depends totally on what values you use really here for R and C. And so those are called, you know, the time constants of the function. Okay, and so we can actually get pretty far here, right? So there is some very interesting math. None of it's that difficult, but we can get a function of time for the charge. You can get a function of time for the current for a charging capacitor. And all we really used was conservation of energy, and that was it. We just added up the voltages around the loop. The loop was pretty simple, and it led us to, you know, these results. And then, you know, we're using some definitions in here, things like that. And so, you know, this works out, you know, pretty nicely here. Okay, so, you know, what else would there be left to do? Well, when you charge up the capacitor and it's full, then what you can do is discharge the capacitor. And usually when you discharge the capacitor, you don't need any agent to be doing any charging. And so you drop out the battery. And so, you know, that might be worth, you know, sort of looking at here. And so, let me see, I called this charging the capacitor. Okay, number 3. So let's go down here and let's call this here number 4. Let's discharge the capacitor and see what happens. discharge the capacitor after it has been fully charged. And we'll take the battery out of the circuits. Okay, and so my circuit is going to, maybe look something like this. I've got two plates, and maybe one plate has got like minus Q0 on it, and this plate has got plus Q0. And when I say Q0, that's at the start of this, and at the start of this, that's Q max. And and then maybe the charged particles will go through some sort of resistor, call that R. And so, this showed up in, the lab with capacitors, that you charge up a capacitor, get rid of the battery, and then hook up the capacitor across a resistor, right? You always want to have that resistor there. And see, now what you really have here is a whole bunch of, little positives here sitting on that plate with equal number of negatives on the other plate, and they can't jump across that air gap, right? They're just not doing that. But the minute you hook up this circuit, the positives can see the negatives. And so they're going to move through the wiring, and then they're going to neutralize, right? Then you lose your charge that is stored. And what you say is that you are discharging through that resistor, right? So you always want to have some of that resistance here. And so what's again, to work out any sort of mathematics here, always go to fundamentals. Usually you don't have to look any further for anything like that here at all. And so there's no junctions. And so really the only fundamental is add up all your voltages and add them up to 0. And so if I just kind of circulate around this loop, I only have 2 elements here. And so I go across this capacitor, and maybe I'm going to cross it kind of backwards. So maybe I got a minus sign here. I'm going to add all these things up, and then I got to go across the resistor. And the resistor, would have, probably a term like this. So really in your textbook, currents go from, how positives would flow, and the positives would flow towards the negatives. And so, maybe, well, I'm just going to guess that the current's doing this, and it doesn't really matter because the signs will be the signs. They'll tell us here. The math will tell us what's taking place here. So I'm going to add up all my voltages. I've got 2 elements. Voltage across a capacitor is Q over C. And then voltage, across a resistor is I times R. And so let's just kind of see where this really kind of leads us here. And so just like before, right, there are some interesting things here. And, the interesting thing here is that Q, that is the charge on the plate, is changing, and so is I. I is changing too. And so Q probably starts off at a maximum value, and then it goes down to 0. I starts off at 0, and then it, eventually will die down too. And so, what do we do here? I'm going to write this as, maybe minus Q all over C equals, I times R. So I'll just put that term on the other side. And once again, I equals dq dt. So I'm going to make that substitution here so I can deal with this equation with just really one thing that is changing on me. And when I do this, I end up with a very nice, once again, separable differential equation. So get all of your Q's on one side and get everything else on the other side. And so I'm going to multiply both sides by dt. And so that'll be over here. I've got dq on this side, and I'm going to, divide both sides by a C over here, and I'm going to divide both sides by that R. So I think I end up with, something that looks like that. And this looks pretty good to me because once again, the two differentials, the dt and the dq, are been separated. So that means that you can hit both sides of this equation with an integral to undo those differentials. And so we're just going to go out to some dummy variable called t, so that can stand for any number. And, charge is going to go from, what you start with, Q0, which is really, the max amount of charge. And it can go down to really anything, right? Eventually it can go down to 0, but we can let Q be any number that we really want to here. So it starts off at some maximum value, and then there's just lesser values, available later on here. And so, on this one side here, we end up with a minus T all over RC. And so, that's not too difficult to deal with. And now the other side is exactly what we had really before, right? You have a dq over q, and so that's really a natural log. And so you end up with a natural log of really q all over maybe q0, right? So you really can write those as a subtraction. I'll just sort of save that that value here, and then raise both sides to the e to get rid of the natural log. And that's just because people just typically rather deal with exponentials than log functions. And it looks like, we end up with something like this, that the charge on the plates as a function of time is an exponential decay, that you start off at time 0 with Q0, right? So at T equals 0, the charge is Q0, which is your maximum that you can get on there. And then it starts decaying after that, right? And so it gets, smaller and smaller and smaller and smaller. And so this is for a discharging capacitor. But that could be worked out, looks like, pretty much, right to, some sort of functional form that looks pretty nice here. And now maybe I'll put a part B here, is let's get the current as a function of time. And so, how do we do this? Well, just exactly what we've done before, that the current is really, dq all over dt. So I'm just going to take the derivative of this function here. And I think, what I'm going to have here is a Q0. I'm going to have an RC, E minus T all over RC. And so there is the current as a function of time for a discharging capacitor. A capacitor that's discharging through a resistor. And so it looks like, it starts off big, and it's an exponential decay as well. So very cool, right? Very simple physics, just using conservation of energy around a loop. That is, some elements, the battery gives you energy, and the other ones are elements that are using that energy as you go across a resistor or a capacitor. And so using that, leads to very, very nice, doable mathematics at this level. And so this is something that we can solve, explicitly, and get very, very nice values here. So yeah, this is very cool here. So so what you really have kind of here in chapter 26 is, using something like Ohm's law, and understanding that I might have a lot of resistors, and if they're in parallel, I know how to deal with those. If they're in series, I know how to deal with those. And then using Ohm's law to find voltages across resistors and to find currents that are going through the resistors. And that was really the first lecture. And then if you start adding some elements like having a second battery inside of a circuit, then it's harder to use something like Ohm's law, and you really kind of go to, the conservation of energy and the conservation of charge, which are collectively called Kirchoffs loop rules. And you can analyze more complex circuits that way. And so actually I went to a very simple circuit here, just a single capacitor and a single resistor. But there's a lot of mathematics here because the charge on the plates, whether it's charging or discharging, is a function of time. And the current that is feeding the plates, whether it's charging or discharging, is really a function of time too. But being very careful using the loop rule, we can actually solve these equations exactly. And so it's very typical in a class like this is that you go to the laboratory, you get a single resistor, you get a single capacitor, and you get a single battery, and you hook up the battery and you watch what is happening. And it's very easy to watch because you can just put it on a computer screen now. And so you can put a voltmeter, for example, across the capacitor, and you can see the voltage climb as you're charging the capacitor. And so you just look at voltage versus time, and typically you see that the voltage go up, and then either start petering out and getting very close to the voltage of the battery, and that's where it stops. And so these things can be looked at very, very nicely, very easily. Eventually I'll probably try to get some sort of activity where we can maybe do something like that here, even though we can't do it face to face. Maybe some way to do this where it makes some sort of sense here. So I'm hoping this gives you some sort of feeling of what's going on in chapter 26 and how you can apply these rules and apply some of the math that you do know to get some very interesting results here. And to a lot of people, an RC circuit is not that important, but it's important in that it's a very good example of using the loop rule and a very good example of using the math to get some very interesting results. And I think a lot of times the engineers use RC circuits because there's time involved, and then they can have something timed, like the windshield wipers in your car and things like that. When there's this intermittent kind of rolling knob that you've got on there. And, just by probably having a variable capacitor or a variable resistor, you can, vary those times very nicely. So, these things have been thought through, and so engineers will, use this type of stuff very cleverly. So very nice stuff here. So give this some thought, work through the sections in chapter 26 and, make sure that this is making sense to you. And I'll see you soon, and we'll talk about how this is working for you, or maybe not. So I'll see you soon.